All right, so as everyone is starting to come in, I think let's just start by sharing the slides. Okay, so warm-up question. How many ways can you arrange 4 different books on a shelf? So yeah, today's topic is combinatorics. So we'll be talking a lot about counting, not so much about probability, but you know, it's pretty fun class ahead. All right, so as the answers roll in, since this is one question, does anyone want to volunteer to explain the answer? Okay, Alec.
So what you have to do is like basically list 4 places, and then since you have 4 books, the first place you have 4 options, and then the second place you have 3 options because you already put a book in the first place, and then for the third place you have 2 options because you already used 2 books, and 4 minus 2 equals 2. And then for last place, you have 1 book left, so you have 1 option. And then you have to multiply these together to get 24.
That's very good. So yeah, what Alex just explained is the basic idea behind a permutation. So I forgot to annotate. So essentially, this is a simple example of something called this, a permutation. And essentially, a permutation is simply any way to order any number of objects. So in this case, you had 4 books and you had to order them in a way on a shelf. So that's a permutation. And today is going to be focused on permutations and its counterpart, which is called a combination. And so a combination is very similar to permutation, except for the order doesn't matter. So essentially, the difference in this problem would be if you want to find a permutation of the 4 books, there are 24 of them. But if you want to find a combination of the 4 books on the shelf, there's only 1 combination of 4 books because the order doesn't matter. It only matters is what the books are. So that would be the difference between a permutation and a combination. And as you'll see as we go through the class, this is a pretty important distinction to keep in mind. All right, so if you have any questions regarding any of these 2 things as we go through the class, please feel free to ask. And we'll go through some related formulas and stuff with this too. All right, sounds good? Okay. All right, so next we have, I guess, a different example of combination versus permutation. So I guess for each of these questions, first, we'll just try to see if you can figure out the answer and then identify which question is asking for a permutation of something and which one is asking for a combination. Right? Okay, so I've had a few people, actually quite a few people, get the right answers. So I guess first I'll just reveal that there were 336 and 56. And so the first one was a permutation and the second was a combination. And I think that an easy way to tell the difference is whether it's specific or not. So for the first question, president, vice president, and treasurer are all three separate roles. So like if this one person is president, and in one scenario, if the person's president, and in another scenario, the person's a vice president, like the two scenarios are different. Whereas in the second question, it's simply asking for a three-person committee. So if a person's in a three-person committee, then and there are no like positions within that committee, then I guess the order in which you choose the three people to be on the committee does not matter. So you'll see that permutations, there are usually many, many more of them than combinations, simply for the reason that a permutation has to be more specific than a combination. And to get these actual values, you can use a similar method to the warm-up, where for the first question, there are 8 ways to choose the president, then 7 ways to choose the vice president, then 6 ways to choose the treasurer, because the person who's president can't be a vice president at the same time, and same for the other positions as well. And so if you evaluate, this is equal to 336. In the second, there are 3 people, right? But the order doesn't matter, which means that you're going to have to divide this first number. And I guess the easiest way to think about it is assume at first that order does matter. Then there are simply 336 different ways in which you can create this 3-person committee. But if you have, let's say, 3 people, these 3 people are called A, B, and C. You can have this committee A, B, C. But you also, when you ignore the order in which they're chosen, you could also have a committee like A, C, B, or B, C, A. These are all counted as different in permutations, but when you're considering them as combinations of people, these are all the same. These 6 are all the same combination. So you just divide this previous number by the number of, you can think of it as like duplicates or overlaps, and which is 6, to get this number is 56. And as we'll see very, very soon, actually, you can also write this problem as 8 choose 3 equals 56, which we'll get to. All right, so are there any questions relating to these 2 questions? All right, then I guess we'll move on to the next slide, which is a bit more general formula describing or generalizing the problem we had before. So this is probably the most important part of combinatorics or counting in the, I guess, in the entire like field, if that's a field of combinatorics. It's kind of like the building block. So this n is just simply a number. You can think of in the previous problem, it's the total number of people. And this k is how many like things or people you're choosing out of these n. So in the previous problem, you were choosing 3 people out of 8. So that was 8 choose 3. That is essentially the meaning of this notation. On the right side, we have this n factorial term, where the exclamation point means factorial, which is n times n minus 1 times n minus 2 all the way to 1. And you also have these other terms like n minus k factorial and k factorial, which is a lot easier to understand when you consider an example. So I think that the easiest way to kind of understand this is just use our previous problem, which is a choose 3. And then n factorial, of course, 8 factorial, right? 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And n minus k, 8 minus 3, that's 5. So this is 5 factorial. And then k is just 3. So it would be like times 3 times 2 times 1. Now, obviously, when we simplify fractions, we can cancel out a lot of stuff. So for example, you can see that this entire 5, 4, 3, 2, 1 section cancels with this 5, 4, 3, 2, 1 section. So you're left with 8 times 7 times 6 over 3 times 2 times 1. And if you recall, 8 times 7 times 6 is exactly equal to the 336 from the permutations. And this 3 times 2 times 1 is just the 6 that we divided by. So if we look at this k factorial term, this k factorial term represents the number of overcounts. It's probably hard to write. The number of overcounting, or number of times you count the same combination more than once. Or yeah, you duplicate it or whatever. This n factorial is simply the number of ways to, actually it's a lot easier to just consider this n factorial over n minus k factorial. This is just the number of ways to choose, the number of permutations of, I guess, k people in n. So if you recall, this one boxing here is the same thing as what I boxed up here. And essentially, this bottom factorial will always cancel out with this ending of the top part, and will only leave this extra section that will always represent the permutation from the first problem. All right. So in essence, the formula for a combination is simply just the number of permutations divided by the number of, I guess, duplicates for each combination, if that makes sense. Okay, so if you are just getting here, so the problems we're talking about look like this, where we have 8 people and we have to choose for the permutations at the top 3 special roles out of them, and for the bottom one, which represents the combinations and the formula that we were talking about, A choose 3 is just any three random people in a committee from this group of 8, right? And 336 is the 8 times 7 times 6 term, and the 56 is what you get when you divide 336 by 6. All right, does that make sense? All right, so I think that's about it for this definition. In reality, what you really know is just need to know the formula, or just any kind of way to conceptualize it to make it easier to understand. That's kind of it. I mean, you'll see this notation a lot. That's why I'm drawing a lot of arrows to it. So yeah. And if you do, in case you do forget, you should probably write this down if you aren't familiar with it, right? So this is going to come up for the problems afterwards. So Be sure to know it. Okay. Examples. This one is a little bit, it's a little bit different, but we can try it out. Okay. Well, the right answer is in the chat, so there's that. So which one is it? Right. So it is 35. As you can see, just like 40,000 is pretty infeasible for how small the grid is. So how is this related to combinatorics? At first glance, it's kind of like you're kind of like counting the number of different paths, right? So when you think of counting, you should usually associate that with combinations, combinatorics, right? And specifically with this kind of problem, the condition that you can only move up and only to the right, it's pretty common, and also is what allows you to solve the problem. Because if you notice, since you can only move up, you have to move up 3 times. So I'll let the U denote an upward move, and the R denote a rightward move, I guess. You have to go up 3 times and right 4 times. And so essentially you have 3 U's and 3 R, not 3, 4 R's. And you have to put them in a row, or just in kind of some kind of string that can describe a path. So for example, this string shown right here with the 3 U's and 4 R's just next to each other like this, it corresponds to this path in black. For example, if I have another path looking like, let's say upright, up, right, right, upright, that would be this, 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 and then like that. So this blue string would, or this blue string of letters would correspond to the blue path as shown. And so you can kind of take a little bit of time to think about how each string or each kind of sequence of letters refers to a unique path, and how you can think of it as like a one-to-one correspondence between a path on this map and some like string of letters. And once I guess that clicks, then this problem just becomes 7 choose 3, where you have 7 spots in this line, right? So 1 for each letter, and you have 3 of the same letter in U and 4 of the same in R. So essentially you just want to choose 3 spots within this line of 7 to place a U into. In this case, there's these 3. Or you want to choose 4 spots to put an R into, right? Where these are the 4 spots that were chosen for this one. And so you can evaluate them, and there you go, the 35. This is, for example, 7 times 6, and then times 5 factorial, or I'll just do this, so 5 times 4 factorial, or 4 factorial. And of course, the 4 factorials cancel, and 3 factorial deals with 6. So these 7 times 5, or 35. And you'll also notice that 7 choose 4 is also equal to 35, because the only differences between the two is instead of 4 factorial times 3 factorial on the bottom, it just kind of flips to 3 factorial times 4 factorial. All right. And you'll notice that this is actually the case for any kind of combination where n choose k is always equal to n choose n minus k. Okay, so someone mentioned water flow method. That is another option for this problem. I guess we can go through it because honestly, I don't use it too much. The main issue with that is that it doesn't scale well for larger problems. So for like a 3x4 graph, it's pretty easy, but once you get to like 15 or like, I don't know, if the dimension is like 15, it becomes a lot more tedious than just using a single calculation. And I'm kind of referring to the water flow graph it's just like, I'm assuming this is what the person meant, is where you can kind of count the ways to get to each vertex along on the graph by adding the number of ways to get to an adjacent vertex before it. I'm assuming it looks something like this. Something like this, I'd assume, right? Where, I guess this is another way you can check your work, where essentially, this is the number on each of these like vertices that I'm labeling. So these numbers just correspond to the closest vertex. They represent the number of ways to get from point A to that vertex. So since you only move up and right, there's only one way to get to each of the vertices on this y-axis. Same for the x-axis. And then to get to this vertex, I should use a color. To get to this red vertex, you can only get to it from adjacent vertices to the left and below it, which are these two. So you just add those two to get this. And for anyone that's actually really interested in, I clicked the wrong one. For anyone that's really interested in whatever we're gonna do next week, if anyone's interested in what we're doing next week, if you notice these numbers, 1, 1, if you like turn it to the right. So I'm actually getting ahead of myself here. If you turn this to the right, not right, if you like turn it to the A to the top and B to the bottom, it would actually look something like this. And so like these numbers 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, as you see from just these like diagonals. This is partially called Pascal's triangle, right? And you'll see that there are some very interesting things that you can come up with using this, and how it's very intricately related to combinatorics. But that's more for next week. It's just something to look into if you're interested. So does anyone have any questions on this topic? All right. So here's a very similar problem, but with a slight twist. Have fun. Oh, and once you figure this one out, try to figure out the opposite, not the opposite. Figure out how many ways you can get from E to G without going through F. All right, so I see why you've gotten the first part, which is 20. There are simply 5 ways to get from E to F and 4 ways to get from F to G. And this is, you can kind of split the problem into kind of 2 sub-problems going from E to F and F to G. And E to F, this is just 5 choose 4 from using like the same method that we used for the problem. And from F to G, it's 4 choose 1, right? Or 4 choose 3, whatever way you want to write it. That's equal to 20. And for the next part, I asked, how many ways can you get from E to G without going through F? And I guess the only way you can really do that is to calculate the total number of paths from E to G and then subtract 20 from them. So there there are 1, 2, 3, 4 down and 5 to the right. So this is 4 plus 5 is 9 total, I guess, directions or moves or whatever. And then 9 choose 4, or again, using that same method. And this is equal to 126. So 126 minus 20 is equal to 106. And that would be the number of paths from E to G not passing through F. All right, so this is the this is kind of a take on a variation of the previous problem, and hope you see that for even this graph, it becomes quite a bit more difficult to use that earlier method that I illustrated with the labeling the number of ways to get there, because it's just simply so much stuff to do, and especially when there are conditions like going through point F or not going through point F, it becomes pretty inefficient to try to use that method. All right, so are there any questions on this topic or questions on this specific problem? All right, so the meeting is going to end very soon, so I'm just going to exit out and then start up a new meeting, and everyone should rejoin. All right, does that sound good? All right. Okay, so as many of you have noticed, I guess, this question it's pretty computationally difficult. So the main idea is that it's 30 choose 3, times 40 choose 4. Where 30 choose 3 is the number of ways you can choose the 3 men on the committee, and 40 choose 4 is the way to choose the 4 women. Right? So I guess the reason why this question is here is simply to emphasize that it's important to know, I guess, or be solid in your multiplication when you're working with combinatorics, because you'll see that, especially when you're working with something like a deck of cards, you'll see that pretty often you might work with something with like 52 choose something or something like that. So that's why I kind of want everyone to be a bit more accustomed to working with big numbers. Or if you don't feel like doing that, you can also use a calculator, although that might kind of defeat the purpose of the whole thing, but you know, you do you. So I'm just gonna write out I guess what you write out the, I'll write out the whole thing and then we'll go from there. So it would kind of look like this. I already factored out like the 27 factorial from the top and bottom of the first one, and the 36 factorial from the top and bottom of the second one. So this would be, I guess, the quickest way to do this. And then afterwards, it's just figure it out, have fun. So I'm not gonna spend any more time on this. The answer is many, many digits. It's this. So if you did not finish, that's okay. You can write this down. So in case you do want to finish it up and check your work, this is the answer. So most problems probably won't be this computationally intense. So that's okay, but just know that it's always a possibility, and just be prepared. All right, so you may or may not. We probably won't though. See one very soon. Oh yeah. Also, I did not do this by hand. I used calculator, so there's that.
I said it was good practice for long multiplication.
Well, it is. It's just, you know, it's good practice. You know, I could do it, but you know, I just don't have to, since I'm not a student. You know, I'm a teacher. I can kind of say what I want. Okay. This is the last of the problems for today on the slides. I think if we have more time, I'll just come up with a few different ones on my own, which would be fun. So let's try this one out. I guess we'll see. Let's see this. Okay. So this question asks, you essentially have 10 puppies and 2 of them can't be in the same group, but you also need to split them somehow into group of 4, group of 6. So it's like a few more restrictions you have to think of how to take care of, essentially. So work on this for a few minutes and then we'll discuss. Okay, so far, no right answers. Not very many attempts either. So I'll give a hint. Instead of, okay, so we know that for this question, we have to deal with these two puppies that are not fun to deal with very clearly. So what if we try to deal with the ones that are not biter and nipper? There are 10 total puppies and 2 of them are problematic, right? So think about how about we, instead of figuring out what to do with them, just deal with them later, biter and nipper, deal them later, and I guess consider what do the other 8 puppies do? Where do they go? And how do we proceed from there? So what do we do with the other 8? All right, so we've had one correct answer so far. So why don't we step through this problem? All right. So I guess what I was trying to get at with the hint is that these other 8 puppies, we can kind of do as we please. We can put them in whatever group and they won't mind, right? And so there's a group of 4 and a group of 6, but we know that biter and nipper have to be separate, right? So this means that one of them has to be in the group of 4, the other has to be in the group of 6. So if we take them out of the equation, this becomes 8 puppies and a group of 3 and a group of 5. Right. If we take them away, this becomes a smaller, simpler problem. And with this, you can just pretty quickly do h choose 3 equals 56, right? This is the number of ways you can put the remaining 8 puppies into a group of 3 and a group of 5. And you're essentially leaving one slot in each group for one of the 2 remaining puppies, biter and nipper. Right. And then since these 2 puppies, it doesn't matter which group they're in, it just matters that they're separate. So we have either biter's in group 3 or he's in the group of 5 or with them. And the same with nipper. So that means that there are 2 different ways that we can put these 2 puppies into the 2 groups. So the answer is 56 times 2, which is 112. So I know that this problem was quite difficult for a lot of you. So please, if you do have questions, ask. This wasn't the simplest, most straightforward kind of solution. You have to kind of like simplify the problem into smaller parts that you can do, that you know how to do, and then kind of let's build it back up to what it originally was. So that's kind of how I would approach this. Essentially, when you're given a lot of restrictions, just try to think of whether those are like how restrictive are they. In this case, this isn't that restrictive. You can kind of like consider it completely separate from the other 8 puppies, and so I think that's the best way to approach it. So I guess this does come with experience. It's mainly just identifying what parts of a problem like are dependent on the other parts and which ones you can kind of just approach independently, if that makes any sense at all. What I'm getting at is simplify the problem and then try to see how you can make it more complicated without making it like more complicated to think about. All right, so I guess this is the main problem that I do want everyone to think about. If they didn't get it, think about like what you were trying to do and how that differs from what this solution is. All right, and just another tip, if you are like, I don't know, completely guessing or whatever, you know that 10 choose 4 is just an upper bound that you can work with. This is actually 210. So if your answer is larger than this upper bound, you know that it's definitely wrong. So if you do want some like a little bit of a safeguard to that, that's your thing. But this doesn't really help you solve the problem. All right, so are there any questions? Comments, concerns? All right, then I'm just gonna, here's the solution, 112. I'm just gonna leave you with one last thing to think about this. And let's just say we have Just a thought experiment, not thought experiment. Let's say we have a round table, okay? Whoa. And we want to sit 5 people around it. So person 1, 2, 3, 4, 5. And there are no other reference points other than this table itself. How many ways are there to sit 5 people around this table? As we're kind of running out of time, to say the answer is 24. And the main idea is that it's 5 factorial over 5 or 4 factorial. It's simply because if this was not a table but like a line, then this is simply 120 5 factorial. But since you loop around, there's no like definite first, second, third, fourth, fifth position. So essentially, you have to divide this 120 by 5 because it doesn't actually matter in the end which person is sitting like in the front or whatever. Another way you think about it is if this number 1 guy, he has his chair bolted to the ground or something. So he's like always here. Then there are 4 other places to place him around and to place other people around. So that's 4 factorial. And since this person 1 is always fixed here, you can't like rotate the table or anything like that, which also is kind of another way to think about why it's 24. But yeah, that's it for this class. Well, if you do have any questions, you can stay on and ask. Otherwise, I'll see you next week. Also think more about this. This is pretty cool, I think. So yeah.
Thank you. Bye.
Bye-bye.
Yeah.
Thank you. Bye.
Bye.